Hello, everybody. Today's talk is the start of Unit 4, in which we will study human energy use and its environmental repercussions. In today's class, I'm going to give you some introductory thoughts about energy use. But before that, I want to present an overview of the entire unit of our energy study. So let's look at that. First, I'm going to start by talking to you about how to think about energy, what it is, how humans use it, the problems that it causes, some of which we've already reviewed, and then what kinds of steps we can take to change our energy use and to reduce its environmental impact. After that, I will talk about fossil fuels, and there we'll be talking about the big three: oil, natural gas, and coal. And we'll be talking about each energy source and looking at how we use it and what the negative effects are of each one, as well as what it is actually good for. And finally, renewable energy sources and nuclear power, you all will be talking to the class about in 10-minute presentations that you'll be giving in about a week or two. So let's get started. Energy is an odd thing to discuss because it is a very abstract idea. Humans were late to discover that they needed the concept of energy. Isaac Newton and all the physics that he invented had no concept of energy. And the word energy wasn't even used in the language, wasn't even invented until the early 1800s. So it is a hard thing to think about. In the physics definition, energy is the ability to do work. Something with energy has the ability to do work. And so a way to say that is it does things for us. In everyday talk, we can think of energy as a thing that does things for us. So, for example, it moves us from one place to another. It saves us labor. It prevents the thermal environment from killing us, right? In other words, human beings could not have moved out of much of Africa were it not for the use of energy to prevent us from dying of cold. And so energy is important to us, and it does lots of things for us. So let's think a little bit more about it. That's a really good question. I want you to think for a second about how you personally use energy every day and think if you can put it into some categories. I'll pause for a second, allow you to turn off the video and jot down some notes. Well, energy is used personally, right? You use it for heating, use it for cooling, use it to transport yourself, you use it to do things for you, use it for light so you can work into the night. And more these days, we use it for entertainment. And I'm sure maybe you've come up with some others, and in class, maybe we can discuss some of the other categories. If you think about it at a larger level, aside from just yourself, if you think about it sort of at the society level, energy is used to move commodities, things that we personally like to have, like bananas or cinnamon or I don't know what else, things that are made in China that we really like having, like iPhones. We, as a society, use it for transport and travel. And we've also used it to increase productivity. Increased productivity is incredibly important to human beings. And I don't know if you've ever thought about it, but I want you to take a second to think about why productivity is so important to the way we organize society. We can also think of energy in two ways. Some of it is necessary for our survival, and other parts are simply used for convenience or pleasure. And those distinctions might become necessary when later on we are trying to figure out ways to conserve or use less energy. We can categorize energy in lots of ways. I've never found any particularly insightful ways for me personally to think about this, but I'll show you some of the ways that it's going to be brought up later on in this presentation. And when you read articles about energy use, you will see these categories used. So for example, transportation versus industry versus buildings. That's one way. Personal versus business/industry versus government is another way I've seen it done. And the way that you'll see later in this presentation is residential versus commercial versus industry versus transportation. So residential being what people do in their homes, commercial being energy used to run a business, industrial to make industrial commodities and transportation to move things around. All energy sources have external costs. The textbook that we use claims that all energy sources are dirty, and that's true to some extent. But this hides the fact that the external costs are very different for different energy sources. We will need to look at the cost of producing energy, as well as how much environmental havoc they wreak, especially when that environmental cost is not included in the price of the energy source. One of the ways we're going to look, obviously, since we've just finished our climate change unit, is do these energy sources produce carbon dioxide? We'll also want to look at do they create pollution, because we will soon be studying environmental health, and creation of energy has created all sorts of pollution problems. And we're going to want to look at what are the costs to human beings as well as to other species on the planet, and also to ecosystems and ecosystem productivity. Therefore, it's important to realize that every energy source has trade-offs, and these need to be evaluated. And so we will do that. For example, as we shall see when we get to it in a few weeks, nuclear power has a very small carbon footprint, which is great. But safely handling and storing the waste has large external costs. You'll hear the term clean energy, and so we want to talk about what we mean by clean energy, given that all energy sources have some negative things associated with them, some negative repercussions. So what does the term clean energy mean? Well, first of all, a clean energy source will not disturb the environment very much or at all. It'll have very few or no emissions of a greenhouse gas. It will not create pollutants. And it will be renewable, so it doesn't destroy a resource base. I think that would make some sense to you. Another way to say this is it will have few to no external costs. What are the characteristics that make an energy source good from our standpoint? Well, first is how concentrated it is. What's the energy density? How much energy is there per ton? Second is the versatility, and how many applications can this energy source be used? Is it only used to generate electricity, or can it be used to make high industrial heat? How versatile is the energy source? Third is safety. How safe is it to handle? And I should ask, how safe is it to have in the environment at all? Not just to handle. We may be able to handle it safely, but low-level pollution might get out and cause us a headache. And fourth, how available is it? If it's easy to get a continuous supply, that would make it a better energy source. A poor energy source would be one that had a high hazard potential, as I was just saying. How likely is it to harm human health? How much environmental damage is caused in the extraction or in obtaining this energy source? And what's its cost? How much does it cost to extract? And of course, we need to include the external costs. And in the textbook, table 10.1 takes a nice look at this for all major energy sources. So you could look at that. As an example, let's look at oil. There are pros and cons of using oil. Some of the pros are oil has a very high energy density. That's good. You get big bang per unit of weight. It's fairly portable, and despite the spills, it's easily and relatively safely shipped from place to place. It's versatile. As you're going to see, many fuels are made from oil. And the current supply in the reasonably short term, the next 30, 40, 50 years, is fairly stable. So those are all pros of oil. The cons are spills. And these are admittedly relatively small, but they have devastating local impacts for a long time. However, it is a huge greenhouse gas producer, and this is a very big con, as we saw in the climate change unit. And finally, it creates many environmental toxins, especially air pollutants, when burned. And the leakage of raw petroleum into the environment also creates all sorts of environmental health issues when human beings are exposed to those chemicals. And we're going to talk about that in the environmental health unit. One statistic to look at, but not the only one, is net energy and the net energy ratio. So let's talk about what we mean by that. Net energy is the total amount of useful energy available from an energy resource minus the energy needed to make the energy available to consumers. And it's analogous to net profit. And net profit for a business is the total revenue taken in minus all the expenses to make the product. And then you have what's left over is called the profit. Net energy ratio takes net energy and turns it into a ratio, obviously, where you have the ratio of the energy produced to the energy used to produce it. That is the net energy ratio, and we're going to talk about that in the next few slides. Conventional oil has a relatively high net energy ratio, and that is one of the reasons why it's such a great resource. One thing before we go on, net energy does not take into account the external costs of energy production. So any external costs are not taken into account. So let's look at some net energy ratios. And in order to do this, we have to look at what the energy is being used for. So here we have it for heating space, which is what we commonly use energy for in our houses and workplaces during the cooler months. We see that passive solar design, which we're going to have somebody talk to us about, has a very high net energy ratio. The amount of energy you have to put in to make a passive solar house is low compared to the amount of energy you get out of that house. Natural gas has a high net energy ratio of 4.9. For every 4.9 units of heat you get from natural gas, you put in a single unit of energy to get that natural gas. Oil, 4.5. For every 4.5 units of energy used, let's say, to drive your car, the oil and gas companies put in 1 unit of energy to get that. Electric space heating of air has net energy ratios that are below 1. So you put in more energy to get that energy than you receive from it. So for every energy you put in for electric heating from a coal-fired plant, you get 0.4 units of heat. That's a bad net energy ratio. Net energy ratios under 1 are basically no payback whatsoever. Now, industrial heat. You've probably never thought about industrial heat, but industrial heat needs to be very high in order to do things like smelt metals. And so, look, this is where coal is so incredible, because coal has a tremendous net energy ratio because it has such high energy density. So it might be that into the future, coal will still be used in limited applications in industry, but not in other places. We've already seen that happening, where coal is used for industry, but it is not used for heating houses like it was when I was a child. And I used to walk down the street on my way to PS 41 in New York City and pick up the coal that had spilled onto the street and play with the coal and arrive at school with dirty hands. But we still use coal to fire electric plants, and that's perhaps a poor use of coal because of all the pollution issues with coal, which we'll talk about later next week. Natural gas and oil, they're good at it, but they're not great. Their net energy ratio is about 5, which is good. And then solar power has a net energy ratio for industrial heat of under 1, a very poor way to get industrial heat. And finally, for transportation, once again, we see that natural gas has the highest net energy ratio, whereas gasoline is also very good. Biofuels such as ethanol, and somebody I believe is going to give us a talk on that, is a very low net energy ratio, and things like oil shale and tar sands also have a low net energy ratio. I think the next thing we want to talk about is energy consumption patterns worldwide. And as you know, we have broken the world up into developed and developing nations for analytical purposes in the past, and we're going to do that again. And if I were to ask you, where is most of the energy used and how skewed is the energy used? Is it mostly used in developed nations where fewer people live, or is it mostly used in developing nations where more people live? And this is an important distinction because don't forget, we often hear that pollution problems are due to population. So you've guessed it already. I'm not going to belabor this. But developed nations, which have about 20% of the world's population, use about 65% of the world's energy, with the US alone using close to 25% of the world's total. That shows you that the pollution from energy usage is probably not a population problem per se. And if we looked at farming as a way of getting a lens into energy use, in developed countries, our farming is done with big machinery, using fertilizers that are made with fossil fuels, and that combination of machinery and transporting huge amounts of food at one time around the country and growing it with fossil fuel intensive fertilizers means that there's a heavy reliance on using fossil fuels in developed countries. In developing countries, there's still much more manual and animal labor used, and so the amount of energy used is much lower. And over here, right here, we can see that in this graphic that the per capita commercial energy consumption is much higher in Canada and the United States than it is in a place like Mexico, Egypt, or India. So much more energy is being used. And finally, it is important to point out that the developed nations are not allowing this lopsided use of energy to continue, and within 30 years are predicted to comprise over 50% of the world's energy usage. And that, of course, is going to happen by two methods. One is per capita energy consumption will go up in those countries. And if developed nations are smart, per capita energy consumption in those countries will go down. But we will see what happens. That increase in energy use by developed countries means a big environmental burden in the future unless renewable sources of energy are used. Here are two pie charts comparing the United States' usage of energy and the rest of the world. And if you look at this, two things stand out. One is the United States uses relatively more oil than the rest of the world. 40% of our energy comes from oil, whereas the rest of the world is only about 34%. And the lack of use of renewables in the United States. The United States uses about 7% of its energy from renewables, but the rest of the world double that at 15%. Other than that, things are pretty similar. Hydropower, 3% in the United States, 3% in the rest of the world. Geothermal, solar, and wind, 1% in the United States, 1% in the rest of the world. Nuclear power, 8% in the United States and 6% in the rest of the world. So pretty similar. Finally, this graphic, which I love, and you should take a little bit of time to look at it. On the left side of your screen, what you see is all the inputs of energy that are used in the United States. And on the right are all the ways the energy is used. And so you can look at it this way. The United States produces about 67% or about 2/3 of its energy domestically, and it imports about 33% of its energy. Now, of the domestic production, about 5% of the total is exported, meaning that 5% of the 67%, or about 1/13 of the domestic production, is shipped somewhere else. Meanwhile, if we look over here, we find out that of our use, about 80% of our use is in fossil fuels, and that only 6% is in renewables, and about 8% of our usage is in nuclear power. And one of the things that I found interesting is that our usages, our consumption of energy, is fairly evenly divided, with industrial being the largest and commercial being the smallest. And transportation and residential are also really important. So that's the United States' picture. And as I said, make sure you understand this. I will probably, on the next test, ask you to interpret this diagram. Some things to note on that. We produce about 2/3 of what we use, as already said. About 1/13 of domestic production is exported. 81% of our energy comes from fossil fuels. Renewables account for about 6.5%. And lastly, I should mention something that wasn't on that graphic, is that per capita energy consumption in the US was about 309 million BTUs. What's a BTU, you ask? And I'm not making this up. It's a British thermal unit. Whereas in the rest of the world, per capita use is about 78 million BTUs. So if you do the math, the average USian uses about 4 times the energy per year as the average citizen of the world. So that's it for today. My goal today was to get you thinking about how you use energy, to get you thinking about how the world uses energy, to get you thinking about different ways energy is used, and to get you thinking about how we might evaluate an energy source as a good or bad energy source. In the next lecture, we'll be reviewing some of the issues we've already seen that arise from energy production. And then we will look at what improving efficiency and energy conservation will mean for reducing our carbon footprint in the world. Until then, study hard.